Welcome back, everyone. Today, we are going on a quest, a real chemist's quest for something incredibly important in the lab: absolute purity. We're going to take a contaminated, messy solid and transform it into a collection of perfect, gleaming crystals. So, how do we even start? Well, if you remember from our last mission together, we learned that impurities are basically saboteurs at the molecular level. They mess up a compound's perfect crystal structure, and that makes it melt over this wide, kind of sad range of temperatures instead of at one sharp, clean point. It's a dead giveaway that something's not right.
So that's our challenge today. We've spotted the enemy, but how do we actually get rid of it? How do we take that contaminated solid and fish out only the molecules we want, leaving all the other junk behind? Turns out the answer is this really elegant and powerful technique that uses the science of how things dissolve.
And that brings us to our secret weapon in this whole fight for purity. It's a fundamental property of matter called solubility. Seriously, if you can get a handle on how stuff dissolves, you can pretty much master purification.
Okay, so at its core, solubility is actually pretty simple. It's just the maximum amount of one thing, we call that the solute, that you can dissolve into another thing, the solvent, at a certain temperature. You've seen this a million times. Think about stirring sugar into your coffee. You add a spoonful, it disappears. You add another, it disappears. But eventually, you hit that point where it just sinks to the bottom, right? That's it. You've hit the limit of its solubility.
But that kind of begs a deeper question, doesn't it? I mean, why does sugar dissolve in coffee at all, but if you drop a rock in there, it just sits there? What's the invisible force that's making that decision? It all boils down to this one beautiful, simple rule. Like dissolves like. This is the golden rule of solubility, and it's all about a molecule's personality, if you will. So these molecular personalities basically break down into two main types. On one hand, you've got your polar molecules. Think of them as having little positive and negative ends, like tiny magnets. They love hanging out with other polar molecules, like water. That's exactly why salt dissolves so easily in it. Then, on the other side, you have nonpolar molecules. They're electrically neutral, pretty chill, and they prefer to stick with other nonpolar molecules. This is why waxy, oily stuff dissolves in things like pentane, but totally repels water. Here's a great way to picture it. Imagine all the molecules are at a party. The polar molecules, they're the super social dancers in the middle of the floor, all interacting, grabbing onto each other. The nonpolar molecules, they're the quiet wallflowers, sticking to the edges of the room, only talking to other wallflowers. The dancers and the wallflowers just don't mix. Like dissolves like. But there's another really critical factor here, one that we can actually control: temperature. For most solids, the deal is simple. You turn up the heat and you dramatically increase how much stuff you can dissolve. Heating up the solvent gives its molecules more energy, letting them break apart the solute and hold way more of it. And this right here is the absolute key that unlocks our entire purification technique. So, with our secret weapon of solubility in hand, we are now ready for the main event. Let's get into the purification ritual itself. It's a precise and honestly almost magical process known as recrystallization. Our ritual follows 5 key steps. It starts with choosing the perfect tool for the job, our solvent. And it ends with harvesting our treasure, those pure, beautiful crystals. So let's walk through this whole journey step by step.
So what is actually happening on a microscopic level? Well, what we're really doing is creating the perfect environment for our good molecules to find each other and self-assemble. As the solution cools down, the molecules of our compound recognize each other, they click together, and they build this highly ordered, repeating structure called a crystal lattice. And because the impurity molecules are the wrong shape or size, they just don't fit. They get kicked out, left behind in the liquid. Now, that first step, choosing the solvent, it is absolutely critical. You're looking for something very specific. You need a solvent that barely dissolves your compound when it's cold, but dissolves it like a dream when it's hot. That huge difference in solubility is what we're going to exploit. And of course, it can't react with your compound, and ideally, it has a low boiling point so it's easy to get rid of at the end. Okay, this is a classic problem in the lab. You've added your hot solvent, your good stuff has all dissolved, but you still see these little specks floating around. What are those? They're insoluble impurities. Could be dust, sand, who knows. How do you get rid of them?
The answer is a really clever move called hot gravity filtration.
You just pour the whole hot mixture through a piece of filter paper. The insoluble junk gets caught while your hot solution, with your precious compound dissolved in it, flows right through. The trick, and this is so important, is you have to keep everything hot during this step. Otherwise, your product will start crystallizing out right on the filter paper, and that's a disaster. Oh, and a little pro tip, if your impurities are colored, you can often add a tiny bit of activated charcoal to absorb the color before you do this filtration step.
All right, now your solution is crystal clear. And the temptation, the urge to just rush, is so strong. But in chemistry, patience is everything. Cooling the solution slowly gives the molecules time to find their perfect partners and build big, beautiful, pure crystals. If you just chuck it in an ice bath right away, you're shocked. The crystals form too fast, and they trap impurities inside them. You end up with tiny, impure crystals, and you've just defeated the entire purpose of this quest.
All right, we've been patient, we've let it cool slowly, and now we have these gorgeous crystals sitting in our flask. It's finally time to collect our prize and see just how successful this quest for purity really was. So to collect our crystals, we use something called vacuum filtration. It's way faster, and it uses suction to pull all the liquid solvent away, leaving our solid crystals high and dry on the filter paper. Then, for the finishing touch, we give them a quick wash with a tiny bit of ice-cold solvent, just to rinse off any last little bits of impurity clinging to the surface. So how do we grade our performance? Well, we weigh our final product. Let's take an example. Say we started with 3 grams of some impure stuff, and after this whole ritual, we ended up with 2.4 grams of pure, sparkling crystals. From there, we can calculate our percent recovery. And boom, that's an 80% recovery. Let me tell you, in a real lab, that is a fantastic result. It means we got rid of the bad stuff while saving most of our desired product. That number is the proof. That's our treasure. And I want you to know, this isn't just some abstract lab exercise. Recrystallization is a cornerstone of modern life. The purity of life-saving medicines, it often depends on this exact process, making sure patients only get the active ingredient, not something harmful. It's the same for the sugar in your kitchen. It's refined using massive, industrial-scale recrystallization to get those perfect little white crystals. So, we did it. We completed our quest, we purified our solid, but like any good adventure, finishing one challenge just opens the door to new questions and new frontiers to explore. Because this raises the ultimate question, right? How can we be absolutely 100% sure our new crystals are pure? I mean, they look pure, but are they? And that brings us full circle. To prove our success beyond a shadow of a doubt, we would go right back to that melting point test we talked about. A super sharp, high melting point would be our final proof of victory. And finally, I want to leave you with a thought. Recrystallization is amazing for solids. But what if your target compound was a liquid? Or what if it's trapped inside a plant, like caffeine in a tea leaf? How do you purify that? Well, my friends, that is a quest for another day, a quest that will lead us into the amazing worlds of distillation and extraction. Thanks for joining me on this journey into purity.